Hello, it's Alan Folmsby here, December 6th, 2019 at 20 hours Greenwich Mean Time. Today I'm going to tell you about iron and how iron was the key to decrypting reality. I used to be a cryptographer, and the plain text is the shape of all the nuclei, and the ciphertext is all of scientific knowledge. So I had to examine textbooks that are copyrighted, and then by using iron as the key to decryption, I was able to figure out the shapes of the nuclei. So I'm going to show you the thought process that I went through to figure out the shapes of every element at a magnification of 20 trillion x. Alright, I'm here in the Maui Theoretical Physics Laboratories, and this video is not about my face. This is about looking at models of iron. So let me turn the lights on so you can see the models better. Alright then, here comes the models. Now the thing is that iron has 26 protons, which I'm modeling as white styrofoam balls. And iron 57 isotope has 31 neutrons, which I'm showing as these little brown styrofoam balls. Now the thing is that I worked on this for a couple years, and just at random you don't really see any structure coming out, but I wanted to do that test. So here's a recreation of the initial tests I did about 2.5 years ago with a random nucleon placement for iron. Alright, now as you can see in this picture here, the protons touch protons. And this was the insight. After considering there's no structure here, that random nuclei, a chaotic dynamic nucleus, really doesn't show anything special about iron. Why, it could be copper for all I know, element 29. But no, this is element 26. Oh, I dropped one proton. Let me get that back up. Alright, so no matter how many times I randomize this, it keeps coming out the same fact. The profound fact of the beginning of wisdom of nuclear structure was that iron has protons touching protons. No matter how many times I randomize these, as long as I'm trying to push them together into kind of a round-shaped nucleus, whites touch the whites and the browns touch the browns. There's 31 neutrons, 26 protons in this example here. So using that knowledge of protons have to touch protons in a stable nucleus, I then drew some conclusions, and I decided to look into the static nucleus theory. I'm surprised so few other people have ever even looked into that, and they're more fixed on the quark theory, which I'm rejecting for this year. So I'm going to show you a little bit more of what iron looks like now at a magnification of 20 trillion x. Oh, yes, here it is, the mock-up of the iron nucleus. And I'm going to just grab my glasses here and take a drink while you look at it for a second. Iron, 57 nucleons. Look, there's structure. A large structure is appearing on the horizon here, like a ring. And on the other side, there's another ring of white protons, and they're both coaxial. Now, what the idea is this, that what if there's a cube at the center of iron? That would be a starting point for a static nucleus theory. Or, you know, a hexagonal close pack. Maybe that's at the center of iron. And let's look at both of those possibilities. We could have a cube. See, we have a 3-layer cube, or we could have 2-layer cube. Like carbon has 2 white protons in the center shell, and then everything else goes outside of the cube. Just like there's 2 electrons in the s orbital of carbon, but a transition element like iron has 3 layers, and it has 8 protons in the center shell, as the transition elements are different than the lighter elements. And that once that cube is recognized as being better than a hexagonal at the center, you also realize that the surface has small gaps that's not like the cube. So let's see how this is composed. Here's the shape of the iron nucleus, but let's look at what a silhouette looks like in the new periodic table. All right, there it is, iron on the right side there. We see that in silhouette there's that 3-layer cube in red of nucleons, and the black is the little pyramids covering each face of the cube. The black is protons and neutrons, and the red is protons and neutrons in this picture here. So I'm going to just go back and take apart the mock-up, and you'll see the cube emerging from underneath the pyramids. Alright, so I can take off one pyramid there, and let's see, there's another one over here I can take off. And there's one on this side, and one on the front, and one on the bottom. So I took off 5 pyramids from the 6 faces. So there must be one more someplace. Oh yeah, there it is. Still one more pyramid to take off the cube here. Okay, and see, it's empty now of all the faces being covered by armor. So let's go back to what we're seeing in the picture on the periodic table. And that's iron is on the right there with the 3-layer cube, and each face of the cube has an equal little pyramid of baryons. So the next thing I wanted to say was that the thought process for putting this together was that the protons and neutrons are spheres. That it's known that the proton radius is around 0.9 femtometers. However, standard science neglected to evaluate a static nuclear stacking attempt. I didn't see, after looking through the literature, I did not see any categorical attempt to stack up nucleons in a static arrangement. They're completely wrapped up in dynamic nuclear theories and chaotic nuclear theories, and that they've decided to ignore anything simple and to focus on quarks and a whole zoo of particles. And I reject the quark theory, and I instead it's sufficient just to have protons, neutrons, and electrons for all practical purposes. Now, the glass bead game was written by Hermann Hesse, and that was an inspiration to me that simple little symbols could be useful in high-level science. Now, one of the facts is that iron has 26 protons and 31 neutrons, total of 57 for one isotope, and a more common isotope has 26 protons and only 30 neutrons for isotope iron 56. So here it is, the picture of the ring of 12 protons on this side. On the other side of this mock-up, there's another 12 in a ring, and it's coaxial. So once I had put that together, and I had noticed that that worked out so very well, I started considering that in the past, physicists have evaluated crystallography for crystals of unlimited size, unlike a nucleus. Now, that's a terminated crystal, I've discovered, that the 57 spheres of iron were not studied by standard science. And they didn't even look at a cube at the center of nuclei, and they didn't look at hexagonal close pack at the center of nuclei. It's all too simple for standard science. There's not enough algebra for them to get accepted as papers. However, geometry is a great branch of mathematics, as the Pythagorean theorem showed, and their school showed the proof is done with geometry, not algebra. Now, I looked at the hexagonal close pack, and it's just not a survivor. If the center of a nucleus is hexagonal close pack, I found that the surface would be a cubic lattice, a simple cubic, which is vulnerable, like on the bottom line here. HCP, hexagonal close pack, if it's terminated, it has a lot of simple cubic vulnerabilities on its surface. So I put together some models of iron, and I'm just going to show you some of that as you read. All right, so I pointed the camera at something else here, and the reasons I'm certain that iron has this shape is that at random, as I showed you, protons form lines of protons. And when I found out the shape that was achieved by having a 3-layer cube at the center and armoring each face, I found, surprisingly, a ring of protons emerging on one side as I put the mock-up together. And then as I finished it, I turned it around, and rotating the model in my hand was like going to the far side of a moon that I just discovered has a second ring on the other side of the mock-up. And it came to me, the instant realization that these two rings are like a transformer, a magnetic transformer with a primary ring and a secondary ring. Okay, and also the stability of a pyramidal cube matches the physical property of iron. All chemists and nuclear physicists are aware that iron is very stable against fusion or fission or decay. And the shape that I've been showing you right over here is just very good for stability. So there's a close-up then, a close-up of iron. So this is from the periodic table of nuclear structure. And you can get your own copy of this at the pyramidalcube.blogspot.com. And what you're seeing in this is the baryons, protons and neutrons. And for iron is a foundation element, which means it's a cube with 6 pyramids on it. And then next to it you see cobalt with one blue proton being added on top of the foundation. Cobalt is a incremental element. And nickel's an incremental element. You can see it there in a smaller version with 2 blue dots for 2 protons that are put on top of the iron foundation. And then later on in the periodic table is germanium, just off to the right farther, which is a different type of foundation element. There you see it. Germanium has also a 3-layer cube on it. And the incremental elements, arsenic, selenium, and bromine, simply add 1, 2, or 3 protons on top of the foundation element of germanium. Now, foundation elements are 18 in number. All of the noble gases are foundation elements. There's krypton. Notice there's no blue dots on it because it's a foundation element, which means it has a simple cube at the center, a simple cubic lattice, and then the 6 faces of that cube on krypton there are covered with a pyramid. And this stacking produces a hexagonal close-packed surface, which has excellent survivability. So let's look at the entire periodic table here briefly. Alright, and we get to see my chin in the picture too, which is great. Now I can tell that, of course, on YouTube, live streaming today, this is all blurry to you. You can't see very much on this. So you should get your own copy of this, and then you can be comparing things like the manganese and copper and gadolinium on the periodic table, and you'll be seeing why these are similar to iron and dissimilar to iron. And the point is that manganese is element 25, iron is 26, and yet manganese is non-ferrous. Iron is ferromagnetic because it has 2 coaxial rings of protons. Now at the bottom you see gadolinium, exclamation point. This proves this is the correct theory of nuclear structure. Gadolinium has 2 coaxial rings of protons. But instead of 12 protons in a ring, there's 18. Now, you can get some documentation online that explains these things that I've been talking about. I wrote this scientific paper recently called Magnetism from Iron's Nuclear Structure, and that was published in the Journal of Nuclear Physics in the March 2019 issue. I'm Alan Folmsby, Master of Science in Electrical Engineering. I have promoted myself to be a theoretical physicist, and you can look at 3D models of iron on the website there, thingiverse.com, for 3D models for your CAD system files. So geometry, this is what I am emphasizing here. So as you see the silhouettes of iron and technetium and zirconium, the form fits function, and the 4 layers of cube in technetium make it unstable because the center of that cube is a vacuum. The elements with 3 layers in the cube are stable because the center position in the cube is a baryon. And the 2-layer cube of nitrogen, for example, while it has a vacuum at the center of the cube, it is stable because there's only one layer of baryons in the cube above that center point, so it has nowhere to fall. So part of this using geometry is that we can have an understanding, a human being, a theoretical physicist can have an understanding of these things not based on algebra or quoting Schrodinger's equation, not based on ab initio energy conservation. This is about integer geometries. And iron, I've modeled the 57 spheres in 2 colors. And I asked myself the question, what if a cube is at the center of iron? So I began evaluating what kind of cube, 2 by 2 by 2 or 3 by 3 by 3 cube of nucleons. So since 3 cubed is 27, I went with that since it's so close to 57. And 2 cubed is only 8, not even close to 57. So 4 cubed is 64, which is too many. So I picked out the 3-layer cube. Now, I noticed that the 27 baryons in the cube just need 30 more to make the 57 of iron, and that the 6 faces would then need 5. So in other words, 30 equals 6 times 5. And 5 is the number of baryons in each pyramid armoring each face. And for symmetry purposes, I've been using lithium 5. And after all this evaluation, I have come to some level of certainty about this. I'm 100% certain that iron's nuclear structure is as I have been describing today. And I've been using inductive logic for other elements. For example, there's iron, and then if you add one more proton, you get cobalt. And you add one more, you get nickel. And one more, you get copper. And yet copper is non-ferrous, and nickel is ferromagnetic. So let's take a look at some pictures here. Alright, there's my mock-up of iron. And here's the little lithium. Alright, that's a better shot. Yeah, there's iron. Now, what I'm trying to say is that this lithium can go on to finish off this cube. And that this then is persuasively the actual shape of iron's nucleus at a scale of 10 trillion x, because of the human intelligence recognizing 2 coaxial rings of protons being very similar to the primary coil of an inductor and the secondary coil of an inductor. It's also like a radio transmitter's transmission loop antenna and the receiver's loop antenna. So recognizing the properties of chemistry, physics, and electromagnetism is fitting the form of the shape of iron, and that other elements are not, then I jump to the conclusion that this is the correct theory. And if we put more of the protons on here, like if you put one here, that would make nickel, and if you put another one, that would be copper, with others on the other side. And so the point is that copper would have a short circuit there. And I have some more pictures to show you concerning this. Oh yes, I'm about to bring it up now. Oh, here's copper. Yeah, over on the Thingiverse, I have shown the copper nucleus. So very much like what I was showing you in iron. Let's see if I can rotate this around. Oh, that's almost right. So you can see that iron is almost like copper, except now copper has a couple more protons there, making a short circuit between the axis of the ring and the ring. So copper has one ring being spoiled and ruined by having that extra proton beyond what nickel has. So let's see, here's another view of the side view of copper, and notice how similar it is to the side view of iron. And these just neutrons form lines that isolate the rings of protons. Now here's another picture of gadolinium and iron. I'll get my mobile microphone going here. Okay. I'm moving over to the gadolinium again here. Oh yeah, here it is. Now you see that the ring here in green are the protons in this model, green protons and white neutrons, and that the iron also is the same. This is 57, and let's see, this is like 174 or something for the how many spheres we're looking at here. And next to it is a little cube 2. All right, it's focusing. Great. There, see, there's 2 protons in the center of light elements, just like there's 2 electrons in the inner shell. All right, so you see gadolinium has 2 protons on the axis in the center there. Now it's stretching out in that direction because the pyramid on top of it is a bigger one than the pyramid on the sides. Now, I'm going to show you how the periodic table is representing that, and you'll see the value of geometry. 3-dimensional mock-up geometry gives insights that the algebra is unable to give. In 1,000 years, Schrodinger's equation never would have told you about 2 rings of protons in iron. So I'm going to go back to the screen here. Here we go, zooming around for you. And I'm going to get to gadolinium really soon now. All right, we're almost up to gadolinium. All right, see, cerium is a foundation element on the left here, which means it has the cube at the center and 6 pyramids on the faces. And you see the red are protons and neutrons, and the blacks are protons and neutrons. They're called baryons. And then any incremental elements like praseodymium or neodymium here have a couple of little blue dots on it for the added protons. See how neodymium is very similar to cerium on the left, but it just has 2 more protons. And then promethium on the right has a 4-layer cube, so it's unstable, as is well known. And then to the right of that we'll find gadolinium. There it is. Samarium, europium, gadolinium. Notice how it's shaped much like cerium, which means on the top and bottom pyramids are big, 4 layers, and the right and left and all 4 sides are the same. They're only 3-layer pyramids, so it's stretched out vertically. That's why in the mock-up in 3D, the best ferromagnetic response has an elongated axis, as this picture will show you. Oh yeah, here comes the picture. So another... Oh yeah, so the double green dots in the center there of gadolinium are elongated in that direction that I just showed you, and in the silhouette where there's a 4-layer pyramid on the top right there, and on the top left is a 3-layer pyramid. That's why for best ferromagnetic performance, it's elongated like that. The next element, say dysprosium or terbium after gadolinium, has even more protons, elongating that, ruining the quality of the ferromagnetic qualities. So terbium's a much weaker kind of magnet. It's paramagnetic. In fact, that's the dividing line between some are paramagnetic and some are ferromagnetic, depending on temperature. And really, I'm recommending new experiments being done to classify based on the nuclear structure which I have defined today. All right, we're about ready to wind up this presentation, but let me just show you a couple pictures here of other elements. All right, so in this one it's nickel, and I've removed most of the neutrons. And so I can, this is in Blender, CAD software. There's the coaxial rings of protons in white, and a couple of neutrons are left in. Now I'm going to just rotate this around for you. There, using this CAD software, you can see the 3-dimensional illusion presented on this display screen in 2 dimensions. And it gives a little understanding of how this thing is put together, a side view of the rings. Oh yes, I'll just go to a different picture here of, I'm starting to simulate a proton, neutron, and electron in this picture with a bond. So here's a proton, isosurfaces, a neutron for deuterium, and on the right, an electron. Now, I'm just going to go back to the ending of the presentation here so that you can have some certainty that the new periodic table of nuclear structure is the correct theory of nuclear shapes. A correct theory gives correct answers quickly and easily. An incorrect theory gives correct answers rarely, like quarks. All right, now here's my schedule for the next things here. Next Monday, I'll have my next half-hour session here, live streaming on YouTube. Every Monday, Wednesday, and Friday at 20 hours Greenwich Mean Time. That's 10 o'clock here in Hawaii with Alan Folmsby, Master of Science in Electrical Engineering, a retired engineer, and a theoretical physicist. Now, the proposed ideas here today have not been approved by educators. Goodbye.